do this that you probably don't already even know how to do just intuitively. So we're going to look at, of the arithmetic with polynomials, adding, subtracting, multiplying, and dividing. We're going to leave dividing for later because dividing is a little bit tricky. I mean, it's tedious. And so that one deserves its own, we'll take a day just for dividing. But this other stuff is really, really simple. Really simple. Okay, adding and subtracting polynomials falls into the category of duh. I mean, they just, all you do is add like terms. That's it. Now you can organize addition and subtraction and multiplication of polynomials a couple ways. And this is the one thing I do want to just address. So if we're going to add using a vertical format, this is really handy. How do you suppose we would add up these two polynomials vertically? By vertically, I mean, like, we can add numbers vertically also, or we can add them horizontally in a string. We're going to add these vertically. Is there anything we got to be careful to do that you can think of? Say it again.
There's no x.
Okay, there's no x, for example, in this one, right? So we want to make sure that we line up the like terms vertically. So we want it to look like that, right? So there would be, we have to leave a column for every power of x. And even if you start with one that doesn't have an x in it, for example, well, it's possible that you may be eventually adding a polynomial to that does have an x. So even if it's not there in the top polynomial, you still want to reserve a column for each power of x and the constant when you're adding up a bunch of polynomials vertically. See, this is a great way to do it if you're adding up a whole bunch of them at once, because, I mean, I could add 7 polynomials up and all I do is just line them up vertically so the like terms are all lined up, and then just add straight down each column, and it's pretty easy to do, right? So this is a handy way to do it. And within the process of multiplying out polynomials, we're going to end up having to, when we multiply big polynomials out, you're going to end up having to add up a whole bunch of like terms. And so this process will still be useful even in the process of multiplying polynomials. Then here it's pretty straightforward. All we do is just add up the number of like terms for each power of x. Okay. We can, of course, also add horizontally, and sometimes for small polynomials, maybe that's just easier to do. If I'm subtracting here, how would I go about doing this one? If I'm subtracting polynomials, what do you think? What are the steps you're going to go through mentally to get this answer? What do you think? Yeah, I could get rid of the parentheses, couldn't I? I can get rid of the first set of parentheses freely because the coefficient is 1. What do I have to do in the second? With the second quantity? Good, I could distribute that -1 all the way through, and then it just becomes adding up the like terms, right? So that, to me, is really the best way to subtract polynomials, is to distribute the -1 and then just add them, okay? The way they do this, I think, is kind of goofy. I wouldn't recommend this. They're saying you just subtract them in pairs, but I don't agree with that. I think it's really better just to distribute the negative sign and add up the like terms. And I won't spend more time on that with you guys. I mean, that's pretty straightforward. Okay, let's move on to multiplication. How about? Any questions on this stuff so far? I mean, I think when you get into the assignment, this is going to be no big deal. Adding and subtracting will be, I'm not even going to have you do very much because I don't think you'll need very much practice. Okay, how do we multiply polynomials? And there are just a couple little things here, I'd say relatively minor, but still helpful. When we multiply polynomials, remember, this goes back to when we started multiplying out binomials. Remember when we started, we called it foiling. When we FOILed out factors in chapter 5, you might remember at the beginning of that, I said, in a way, I really am not fond of the concept of FOIL, because FOIL only works for multiplying binomials. This is a binomial because it's got 2 terms, right? Poly means many, bi means 2, and then when we talk about nomials, we're talking about numbers of terms. This would be what kind of polynomial, if we had to name it? trinomial, yeah. So if I multiply a trinomial times a binomial, FOIL doesn't work. But the process of distribution always works. So, yes, sir?
How Mrs. Wilson showed us to do it last year
Mhm.
is to make like a Punnett square. And, well, it wouldn't be a square for this one.
It'd be a rectangle.
Yeah, but like you put like the first one all on the top and you put
Second one.
-3 and then
Yeah, and you can do that. You can make a box like this where you put the terms up here and the terms here, and then you just do that, fill them in. Yeah, and that's fine to do. If you want to, you're welcome to. I think for you guys, it's overkill. I think a lot of times when you get into doing algebra work with polynomials, it takes too long and it's too cumbersome. I think all you have to do is just this. It's just distribute. Okay, and I think that's going to be. Was that what you're going to say?
I was going to say, can't you just multiply it out with multiplication where you put like the first one on top and then
You can, yeah, absolutely. You can line them up. We can line these up vertically or horizontally. We're going to go through a vertical one real quickly. A lot of times, multiplying horizontally is sufficient if they're relatively small, like these. These are pretty easy to do horizontally, but when you get big, great big polynomials, I'm not going to have you do a ton of those because they're just tedious. But I'll make you do one or two just so you get used to it. Then multiplying vertically is a great idea. If we multiply horizontally, the one thing I'll say about this is it's generally easier to distribute from the smaller polynomial, and by smaller I mean number of terms, not degree, but the number of terms in the polynomial, to the bigger one. So for example here, we would distribute the x all the way through first. And what would we get if we did that? So we're distributing from the binomial to the trinomial. If x distributes all the way through these, multiplying powers of x by x just does what? Yeah, it bumps the power up by 1, doesn't it, in this case? So I'm just going to get a negative x cubed plus 2x squared plus 4x. Now here's where I would urge you to always maintain columns for each power of x. Even if we had skipped one in here somewhere, keep that column open. Okay, and you'll see why in a second. When I distribute the -3, what am I going to get? So from left to right, -3 times -x squared would be 3x squared. Now, see, look, I'll line it up vertically with this one. Now, you see why you want to keep all those columns, right? Then it makes it really easy to add up the like terms. -3 times -2x, -6x, and finally -12. And then all I have to do is just add them up vertically, okay? So, and that'd be the answer. Yeah, so our answer would just be -x cubed plus 5x squared minus 2x minus 12. Okay. Now, could we have predicted some things about this? I would argue that you could have easily predicted the degree of the polynomial you were going to get back from this. What's the degree of this first polynomial? 2. What's the degree of the second polynomial? 1. So does it make sense that the degree would have to be 3? Okay? Because the most powerful term I'm going to get is always going to be the one I get when I distribute between the most powerful two terms. Does that make sense? I'm going to get a bunch of other terms that are going to get added up, and right? I'm going to add up like terms. There's a bunch of other junk in here, but I know that first term, that first term is going to have the most powerful one. The leading term has to have a power of 3. Okay? All right. So doing this, if we line these up vertically, and that, like I say, very helpful for big polynomials. If I line these up vertically, it's just like normal long multiplication. I'm just going to multiply the -3 all the way through, right? And I'm going to get my -12. I'm going to get 3 times 2x is 6x, or -3, sorry. -3 times -x squared is my positive 3x squared. Make sure that once again you start off with columns for each power of x. Then we just distribute the x through and line up the results vertically with the original results, right? And same process we just did. Okay. Right, see how that works? Multiply the x through, there's my 4x. There's my 2x squared, lines up with the x squareds. There's my negative x cubed, lines up in its own column. Add them all up, and that's the answer we got. Okay? Okay, horizontally we just did. We can skip through that. Okay, what if we want to multiply three binomials out, or 3 polynomials out? They don't even have to be binomials. What are you going to do? Exactly. Yeah, you have to. Remember, we always multiply products in pairs. Have to multiply things in pairs, so you must do this in steps of 2 at a time, right? So we could, for example, FOIL out the first 2, right? Get an answer, and then I just distribute the smaller polynomial through that, and like we just did. Okay? No big deal. I won't even go through the steps. You get the idea, though. It's got to be 2 at a time. Okay? Okay, some patterns. Here's what I want to. These are I'm gonna make you guys do. And I should have done this earlier. I did it with my other Algebra 2 class, and I didn't with you guys, and I probably should have. This is stuff I would argue if you want some feedback about how just preparing to be the best student you can, as you move towards college. This is the kind of stuff that I think you need to be sort of doing. Like, for example, last chapter. I'm going to tack some last chapter stuff in there too. Just a few things. But I think you ought to have, and I think I mentioned this to you, you ought to have like a stack of rubber banded stacks of index cards for memorizing stuff that's useful, that's just good to have this working knowledge. Like, for example, the 3 forms of quadratic functions. I think you all probably know that. But those are things that you ought to make those resources so you put them in a shoebox and have them there to use later if you need to. Quadratic formula, stuff like that. I'm going to give you, in fact, it's already up there. I gave you a short memorization assignment. You're going to do a quiz on that. Let's just say, let's do it Friday. How about? I mean, it's easy, 100%. I'll even make it worth like a 25-point test grade. Okay, but I'm only going to let you do this one twice. Once Friday, and I'll let you do one retake, say, right before spring break or something. Okay, but that's it. And then no more attempts. That's it. But all you have to do is just memorize some stuff. And you'll see what the stuff is on the assignment. It's all stuff you probably already know. Here's the additional stuff I want you to memorize, because this you use a ton. The sum and difference formulas, these are just their product patterns, multiplication patterns for polynomials. Okay, this is a really key one, and we've already seen this one in reverse. Okay, look what that is. This is also called a conjugate pattern. It's a conjugate pattern because, look, a plus b and a minus b are conjugates, aren't they? Right? Whenever we multiply conjugates together, take the product of conjugates, we always get what's called the difference of squares. Okay? So, does that make sense? Right? So x plus 3 times x minus 3 always gives us back first squared minus last squared, right? So x squared minus 9. Now, we did that in reverse in chapter 5. That was a factoring pattern that we used, right? Difference of squares. If we saw that something was in the form a squared minus b squared, then we could break that apart into an a plus b times an a minus b. We didn't spend a lot of time on that. We'll spend more time on it this chapter. So there's one. First pattern you must memorize. The sum and difference of squares patterns. Okay. The next one is square of a binomial. Okay, this one, you can really do this in one formula if you would prefer it. I would always prefer that you do. We really only need the top one, and I'll show you why. If we have, here's our pattern for a binomial expansion. If I have a plus b squared, if I know that equals, do you remember what it was? It's on the screen. Here. A squared, plus, say it again, plus 2ab plus b squared. Good. That's all you really need, because b could be a negative term, right? So for example, if we want to use that to expand x minus y quantity squared, what is that really doing? Well, in this case, a is x and b is negative y, right? I could think of that as being x plus negative y quantity squared, right? And it would just look like a squared, which would be x squared, plus 2 times x times negative y would be minus 2xy, you see that? Plus negative y squared, well, anything squared is positive. See what I'm saying? So really, that's the only one you need. Sometimes people like to include the pattern a minus b squared, and all that does is just change that first sign. Okay. On the memorization quiz, you'll have to know both of those. So you'd know that a plus b squared is a squared plus 2ab plus b squared. A minus b quantity squared is a squared minus 2ab plus b squared. So there's the second of two that you need to know.
These aren't gonna be imaginary numbers though?
No, these won't be.
The variables, I mean?
The variables, well, variables could be anything. They could be,
Why don't you just leave it at minus y squared? Because if it was like negative 1,
Because if it's minus y squared, it would be a negative number anyway.
right, so I mean, because you could have, see, we could be doing things like this. The point is just that you're going to want to expand things like x plus 3 squared, right? We would now know that's just equal to x squared plus 2 times x times 3 is 6x plus 9. Or we could do something like 2x minus 5 squared, right? And what's that going to be if I expand that? Yeah, I'm going to get 2x quantity squared, right? This is the most common mistake people make on this, is they forget to square the 2. So there's my a squared, right, minus 2 times a times b plus b squared, right, which would look like this whole thing is going to be 2 squared, which is 4 times x squared, minus 2 times 5 times x is going to be 20x, right, plus 25. You see what I'm saying? So that's why. But I just always remember, honestly, I know them both, of course, but I just remember a plus b squared, and b could be negative, right? If b's negative, it just turns into those minus signs. Big deal. Because a negative number squared is always positive. Okay, is that clear? I'm going fast for this group, because I feel like I can, but I want you to stop me if something I said wasn't clear. Does that make sense? Okay. Okay, so, yeah, question?
Oh, no. I'm gonna take the picture of that
Oh,
thing.
this will be up there today. It'll be available. So here are the other. So these go together. Binomial squared. Yep.
well, I was meaning like if b was like square root of -1, and if you squared that, then it would be negative.
Oh, right, exactly. So that's.
That's what I was asking. Like, if they're not, none of these are going to be imaginary.
Well, they could be. They could be, but if they're imaginary numbers, you'll know how to deal with them, because then if the b includes an I, right, then it's going to make that positive, right? When you do the b squared, I see what John's saying is this. Well, what if you had something like x plus I quantity squared, right? You're going to get back x squared plus 2ix plus I squared, which is really just a -1, right? Yeah, and that's fine. The pattern still works.
Well, would it be the same if there's like if there's x minus I squared?
Sure. Yeah, then it would just be the same thing. Then that would just be a minus sign right there. Yeah. Okay, and then the last one is the cube of a binomial. Oops. Come on. Okay, cube of a binomial. And this one, it's got 4 terms. You're probably not as familiar with this one, but it's no big deal. What is this doing here? A plus b quantity cubed, you're getting, a cubed plus 3a squared b plus 3ab squared plus b cubed. Where are these numbers coming from? For you guys, I quickly want to show you a trick here that allows you to actually expand any power of binomial within reason. There's a formula called the binomial, for the binomial expansion. that is kind of a weird looking formula that we're not going to deal with right now. But I'll show you a trick called Pascal's triangle, which allows you for relatively, anything, let's say, less than a power of 10. It allows you to get the expansion really quickly. It goes like this. Okay, here's Pascal's triangle. Pascal's triangle is just it's a triangle, and the sides of the triangle are all ones. So the first layer, and this is, by the way, this is the layer that goes with 0. Okay, we'll call this n equals 0. This is n equals 1 is going to have that row. N equals 2 is going to have, whoops, sorry. It's going to have ones on the outside, and then on the inside, whenever you get inside numbers, what you always do is add up the two numbers diagonally above it. Add to that number. So this one's going to be a 2, right? When I get down to the n equals 3 row, I get a 1 and a 1, and now I've got room for two numbers in here, right? This one's going to be a 3, and that one's going to be a 3. Okay, are those numbers looking familiar? So the n's are going to be the powers of the binomial expansion, is what it turns out. And these are going to be the coefficients, right? So we'll go down maybe just one more, and then we could go as far as we wanted to, though. If we do n equals 4, we get our 1s. What's that number going to be? 4. What's that number going to be? That number. Okay, notice that these numbers, of course, are symmetrical, right? We could draw like an imaginary line down the middle, and we get symmetrical numbers on either side of that line, don't we? Right? And we'll just do one more. 1. So what are the coefficients going to be for n equals 5? 5, 10. Okay, now what do these things do? So what this is saying then, we'll take, for example, this row right here, because that's one that we're working with. Okay, this is how you expand a plus b, a plus b cubed when n equals 3. These are the coefficients. Okay, what happens to the powers of a and b? Well, here's how you can think about this. The sum of the exponents always has to be 3. But we're going to start with all the power weighted towards the first term in the binomial and end with all the power shifted over to the second term. Okay, so for example, this first one's going to look like 1a to the 3, b to the 0, plus 3, a to the 2, b to the 1. See the pattern? Plus 3, a to the 1, b squared, plus 1, a to the 0, b to the 3. Well, what's anything to the 0? 1, right? So doesn't that just look like that? See how we get those? Okay. That's how we get the coefficients and the powers. And so we would know pretty quickly then, if we go back to our little picture here, so you guys tell me if I wanted to expand something out big, like if I wanted to expand out a plus b to the 5th, what am I going to get? Okay, times b to the 0, but that's just 1, isn't it? Plus, good. 5 times b to the 1, we just write as b, plus plus good plus okay, and you kind of see the symmetry in that. Isn't it cool how it does that? Notice that each of the like coefficients just have the sort of the opposite powers of a and b, right? So, which makes sense, it'd have to be that way, but it's just kind of, there's a pleasing symmetry to math when it does stuff like that. It always just works the way it's supposed to. Okay, so going back here, so this is one that's, now that's pretty easy to get, right? What happens with the minus sign? Notice how the minus sign gets introduced. A minus b is the same as a plus negative b, right? And so notice that the negative sign only appears in the terms where b has an odd power, right? Because a negative number to an odd power is negative, right? But a negative number to an even power is always going to be positive. See how we're getting that? Right? So really all we've done is we've just taken this first pattern, and instead of adding positive b, we've just added negative b to it. Right? Okay? So that we really get 2 for 1 there, don't we? And probably the best way to do this is just to put a plus or minus sign there, there, and there. You can do them both in one formula. Right? The minus sign only goes with the terms with the odd powers of b. And it did the same thing, by the way. If we go back to the previous slide, it did the same thing when we squared out a binomial, didn't it? If you look right here, look down here, the negative sign only went with the b to the 1 term, right? Because the b, here the b is squared. What's the power of b there? 0. Is 0 odd or even? It's even. It is even, believe it or not. 0 is an even number. Yeah. Okay, so I think, what's that going to, what's that going to be? Real quick, see if you can just talk me through this. So we're going to get x cubed plus, plus 3, see if we can get it simplified. 3x squared times 5 to the 1. Everybody see that? 3 times x squared times 5 to the 1. So what's that whole term end up being? 15x squared. Okay. So we get x squared plus 15x squared. What's the next term going to be? Because a is x and b is 5, right? So we're going to get 3 x to the 1 times 5 squared. Well, what's 5 squared? Times 3. Right? And then finally plus, which is, so there it is. Right? Okay, there's our expansion. Okay. Make sense? Okay. All right, that's probably